that are earbud in. So if that resistor up there drops all the voltage, then it's saturated. If that resistor up there drops no voltage, then it's cut off. Right? You understand that? So we can make these act like an electronically controlled switch. So where do y'all run these things at? All over the place. All over the place. In fact, there's no telling how many transistors. Right now, the microprocessors that we're using now has an equivalent of about 8 billion transistors in them, acting as what? Switches. They're digital devices, all from. So we understand current. What's the biggest current flow in the transistor? The emitter current, followed by the collector, followed by the base, right? Base is the smallest. Everybody okay on that? 3 regions, everybody okay? So 3 regions, saturation, it acts like a what? Closed switch. Cut off, the transistor acts like an open switch, and in the active region, it acts like a rheostat that's electronically controlled. Everybody okay on that? We talked about beta. Beta is the current gain, and we unfortunately, so one of the main transistors we're going to be dealing with is the 2N3904, which is a small, it's in a TO92 case. It's a small transistor. Doesn't buy a lot of current. And this is the problem. We can buy this in at least 3 different packs. These are absolute maximum ratings. What's the absolute maximum rating? The absolute maximum ratings. We saw those on diodes. What's the absolute maximum ratings? Before it blows, yeah. So here's our breakover voltages, guys. So these guys are solid state devices. They got bias on them, right? When they're reverse bias, we still have a path through there. If we break over, then it's going to cause all types of problems, right? So voltage collector to emitter with the base open. Voltage, so O means the other lead is open. A voltage collector to base with the emitter open. A voltage emitter to base with the collector open. So the best we can do over here is what? 40 volts, 60 volts, 60 volts. We'll come back and look at that later. What we're trying to do is right now is trying to find beta. This current gain. IC over IB. Do y'all see any beta in here? So this is electrical characteristics. So this is where the beta should be at. HFE. Yeah. So this is what I was telling y'all last class. Even though books call it beta, in data sheets, normally it's going to be called H of FE, which is the hybrid transfer ratio with the emitter common, what all that garbage stands for. So this guy here could have a beta anywhere between, this is the worst case, would be what? 30. And the most it could ever have would be what? 300. So instead of, and we'll look at this, why we have such a range. So this range can be anywhere between 30 and 300, right? You understand? So what we'll do, we'll show you how we can design a circuit that would actually give us the beta that we want. But we never can get over what? We never can get over 300, and we never can get less than 30. For saturated switches, guys, we would use 30. And then for active region, we would, okay. That was good on the remembering that. So DC beta is a constant ratio. Once we establish it, called the current gain and is usually designated HFE on data sheets. So good catch. So here's the beta formulas, and these are transposed, right? So this is the one we remember, then we can put it, and what's nice about our formulas is once I know one formula, then what can I do? And these should be in your data sheet. This should be in your formula sheet. I don't know. It's on. I think it's on the back. Now, what's nice about most of our formulas, just about every one of them are three-term formulas, right? And once you've got it in just one of the formula, one of the formulas, then you can just put it inside what? You can put it inside this triangle. It's not really a triangle. And then we can use it to get the other formulas, right? So that means we know beta is equal to IC over IB. So what would IB be equal to? IC over beta, right? Yeah. And then what would IC be equal to? Yeah, beta times IC. Are we okay there? And we won't talk about alpha right now. There's and hopefully this works, guys. This is new. We used to have a software package where you could actually simulate circuits. It was called Electronic Workbench. Unfortunately, it was a 16-bit application. And when they came out with Windows 7, they dropped all support for 16-bit applications. So what that means, if we run that application, we'll have to run it on a XP machine. That's the best it will do. What they did is they changed the name to Multisim. And what's nice about this guy, if it boots up, they actually have you can actually sign up for this and actually play around with this for free. And it's very expensive if you register the package. And we'll see if this works. Come on, let me log in. So you would go to what? Sign up for free. Which is pretty neat. And you can actually save your circuits also. So here's a circuit I saved. Now, right now, we're going to start off with a 2 supply bias. Later on, we'll show you how most of this is done. It's done with if I can figure this out. Like I said, I'm used to this one. And then once you get your circuit built, oh, there we go. You understand where thing it says open circuit? I started using this yesterday. Oh, there we go. office computer. Here's your components. So this would be your power supply, of course, commons. These would be your power supply. So what we're doing is working down inside these transistors right now. So what I did is I pulled a PNP transistor. This is a 5-volt supply. This is the potentiometer. What am I going to do with my potentiometer? Yeah, I've changed voltage over to this resistor, right? Okay. And once you get it set up, we have a voltmeter here. So this is going to measure our base. This is going to measure the voltage here. I don't know. I had a voltmeter over here. This is measuring This is measuring base current. This is measuring emitter current. We can put another ammeter up here. So we'll put an ammeter right there. That should measure collector current for us. And then once you get it, you can come up here and start your simulation. Let's see if this works. So what I'm doing is I'm sliding the potentiometer, and you can see my voltage is changing. No, it's not working. Y'all see what's going on? This guy right here is staying at 5 volts, even though I'm moving my pot. So I'll try to figure out what's going on here. What's that? No, I'm not gonna be able to see. I'm not gonna be able to. Yeah, I can take a break. Yeah, and I'll never. I'm not. I don't want to impress y'all anymore, so I'm not gonna do it again. I don't want to make y'all feel bad. Oops. Okay, there we go. It's working. So right now we have 0 votes, and then notice our current is down in what? Can y'all read that? Let me zoom in. 15,000 PA picoamp. So basically, this guy's not conduction, right? That's just leakage getting through it. So what I'm gonna do is I'm gonna come over here. I'm gonna set my angle. So what it's trying to do is it won't let me. The slider is not working. Is what it is. So this is 1%. So here we have 5 votes here, right? You understand, right? You understand that? Notice my emitter current is. Oops, got to go back down one, guys. So my collector current is 15.89 milliamps. My emitter current is 15.3 milliamps. So what's the difference? I can't, it's not going to let me draw. Why ain't this current and this current the same? So if I got 15.3 milliamps right here, why don't I have 15.3 milliamps right there? Ignore the sign. I got my meter hooked. Yeah, this is an amp meter. You can't see the actual arrow. This is where the meter is actually installed. Okay, so I got an amp meter right here that's measuring base current. I got an amp meter right here that's measuring emitter current, and then I got an amp meter up here that's measuring collector current. How many volts do I have at the bottom? Well, we don't need. What's that? This says it's got a beta of. It's telling me it's got a beta of 100. That's the beta, yeah. So it's saying I got 100 amp. If I did 100 amps for every 1 amp of base current, a beta. So if this right here is a series circuit, sorry guys, why don't this amp meter and this amp meter show me the same thing? This is 0 volts down here, by the way, Brian. That's common, right? So that's 0 volts, and you can't see it. It's up here. Over here, I have 4.9 volts. I did have a voltmeter right there, so over here I'd see about 7/10, right? So that means this guy right here. But notice this resistor up here is only dropping what? 160 millivolts. So what would I have across the transistor? Well, you're looking at the base. You're looking at the base emitter junction, and I'm over here talking about a complete junction already. So what you need to do, guys, when you look at these guys, when you look at these, where's my PowerPoint at? When you look at these, what you got to do is look at 2 different circuits. So what we got is right now we've got this circuit right here. So when I look at that collector circuit, I'm looking at this right here. So here's, right now we'll call this RC. This is the collector resistor. And then down here, I've got my transistor. And of course, it can do one of these things, right? You understand that? I come over here and I've got, what it was it, 12 volts or 15 volts? Okay, 15 volts. This guy right here is dropping 106 millivolts. So how much would be dropped across the transistor? Kirchhoff's voltage law says the sums of the voltage drops in a series circuit have to equal to the applied voltage. Okay, so what would this, if this guy's only dropping 106 millivolts, how much is being dropped across the transistor? Yeah, now 14.9 volts, right? So is the transistor cut off or is it saturated? If it was saturated, it would drop almost 0 volts. Here it's dropping the entire voltage, right? You understand? So the transistor's cut off. Now, what you have to understand, a transistor is not an open switch. A transistor is a transistor. There is a path for current to get through there. So even when it's saturated, it will not drop the applied voltage. So this is just current that's leaking through it, right? You understand that? Yes or no? So it's cut off. Yep. No, it's just that a transistor can never, we say it's cut off, but there's always a path. So you're coming through here, guys, and it's a semiconductor. And when we draw this thing out, we come over here and we draw it. When we draw it in the block diagram, we say it looks like this here. So an open switch does this. There is no path through there, right? But this is an NPN, right? That's ENP. And I've got 15 volts capability sitting right there. And this over here is connected to ground. Is there a path through that transistor? Is there a path through that transistor? Okay, so that means it's cut off, but it can't. There's still a path through it, right? You understand? So what we're saying is there's a little bit of current that always gets through it, even when it's cut off. But this up is 10K resistor up there is only dropping 106 millivolts. So how much current would be getting through there? So that's IC would be equal to 106 millivolts, divided by 10,000 ohms. So how much current is leaking through there? Not very much, right? We're down in the what? The nanoamps, right? But there's a path through there. So that's what you got to understand. Transistors are never really, even though they're cut off, there's still a path to do what? To get through it. But how much would that be? 106 milliamps divided by 10,000 ohms. Anybody done that yet? Yeah. Yeah, a microamp. So basically it's nothing, right? You understand? But we need to understand that transistors are never, there's always a what? There's always, is there current flow through the insulation of a conductor? Is there current flow through the insulation on a conductor? Yes. There's a path. We call it volumetric current, but there's a path. There's current flow through the insulator. It's just that it's so dang low, what? It don't hurt anything, right? You understand? So yeah, if you've got a path, if you've got a difference of potential, and you've got a path, there's going to be current flow because it's always I is equal to V over R. It's just that R is extremely high, right? You understand? So the R of the transistor is extremely high. It's dropping 14.9 volts at 106 milliamps. So R of the transistor right now, R of the transistor would be equal to what? R is equal to V over I, right? So that's 14.9 volts. And my drawing thing is real slow. Divided by 106 milli. So what would be the actual resistance of the transistor right now when it's cut off? What, 140 watt though? What? Can't be ohms. I'm taking volts and divided it by milli. So I got to come up with an answer that's a lot bigger than what I started off with, right? Oh, that's not milli. That's millivolts. What was our current? Sorry. Thank you. What was our current we calculated a while ago? There you go. Thank you. I got myself totally confused. But I knew the answer was wrong, right? What is that? 10 point, 10.06, right? I got a zero in between those. Oh, 10.6. Understand. I got it now. Y'all got to take care of me. 0.6 micro. So that's more like it. So I knew the answer had to be right. So I knew it's going to be. So what resistance does the transistor actually have right now when it's cut off? Yeah, meg. So what we have to understand, there's always current flow through the transistor because there's a what? There's a path, even though it's cut off. So let's see if we can saturate it. So when we saturate it, what should we expect to see? Zero out, but is it ever going to be zero? Can a transistor fully saturate? No, but it's going to be real, real low, and that's a good point too. So I'll come up here and we'll saturate it. So we'll go ahead and set it to 100%. So now notice my collector is dropping all the voltage. So according to this, how much voltage you have across the transistor? When you have voltage right here, it's usually going to be on the range of about 10 volts. So usually when a transistor saturates, it's always going to drop a voltage, right? You understand? Because there's always something in between there. Here it's showing it's dropping nothing. Are we okay? Yes or no? Now we'll put it in the center, so we'll put it at 50. We'll put it at 5K. I'm sorry, 50%. This is the way I'm having to do it. Now the thing's in its active region. Notice the emitter current and the collector current are not quite the same. This is 13.4. That's 13.67. Why is the collector current less than the emitter current? What's the formula for collector current? IC equals to not times. There's no times. It's addition or subtraction. Minus. Remember, and this is what you remember, is what is the most current in the transistor? No, the biggest current in the transistor is the emitter current, right? Because the emitter current is not only supporting the collector current, it's also supporting the base current. So notice we have 32 we have 13.4 emitter current. And if you subtract this from that, you should come up with pretty close to the same answer. So IC is equal to IE minus IB. Remember, biggest current is what? Emitter, followed by the what? Collector, followed by the base. So look, I'm putting 132. I'm putting 132.7 microamps of base current. I'm getting 13.27 milliamps worth of collector current. If you took this and multiplied it by 100, you would come up and get that because that's the beta of the transistor. So the beta of the transistor does not give you the emitter current, it gives you the collector current, right? You understand? And we know the collector current is going to be slightly less than the emitter current because the emitter not only supports the collector current, it also supports the base current. So what would we have, what voltage would we measure across our transistor? This resistor right here is dropping this is the voltage drop across, that is the voltage drop across the transistors, guys. Because look where I'm taking my voltage measurement at. I'm putting it right here. So this is, can you see what I'm talking about? So if I'm taking my voltage measurement right here, and it's relative to this guy right here, then that is 1.72. So is it in the active region? Is it cut off or it's saturated? No, this is current. This is not voltage. The meter voltage is 0. And all my references, if you looked at the meter when I set it up, yeah, if it was saturated, it would show the transistor would drop almost 0. So here's saturated. So the transistor has 106 millivolts across it. You understand that? So saturated, it acts like a closed switch. Okay. So what we have is, what we're doing now is we're taking it between saturation and cutoff, right? Okay. So what we're doing is we're going to treat this thing like a switch. Okay. So here's the base. The base is controlling the switch. Here's the emitter. And up here's the collector. Okay. So when we saturate it, we close the switch. So what voltage would we measure across the switch? So how much resistance does a closed switch have? How much resistance does a closed switch have? So if I went over on these light switches right now that's running these lights, and I put my meter across those light switches, how much voltage would they show me across the light switch? So how much resistance does a closed switch have? Okay, so voltage drop is equal to I times 0. So how much do we drop across a closed switch? 0. So if I went on these light switches over there with all these lights turned on and I put my voltmeter across those switches, what would it measure? It would measure 0 volts. It would measure 0 volts. And this gets a lot of people killed, right? You'll go and say, well, let's see if there's power. I need to change my switch out. They get their meter out. They put it across the switch. It measures 0 volts because the switch is closed, right? And how much voltage should be across them when it's open? So how much resistance does an open switch have? Okay, so that means all the voltage appears across an open. In a series circuit, right, you understand, all the voltage appears across an open. No voltage appears across what we call a short. It's not actually a real short. So that means if I saturate my transistor, how much voltage is it going to drop? Well, technically, if it was a true switch, it would drop 0 volts, but it's not a switch. It's a transistor, right? It will always drop a little voltage when it's saturated. Yeah. So saturated, we're going to look at approximately around 100 millivolts on a transistor. But what we're going to do is we'll look up the data sheet. The data sheet will show you the saturated voltage drop. Now, when we open the switch, then what are we going to have across our transistor? So my voltage collector to emitter, so this tells you how to measure it. So this says you put your common on the emitter, and we're measuring to the collector. So saturated is going to be equal to approximately 0, but it'll never be 0. If we measure it across a transistor and it's powered up and it measures 0, you might have to take the thing out and throw it away because it's going to be either it don't have power applied to it or it's shorted. So it's going to be a watt. So saturated, it's going to be a watt. Approximately what? 0. Is it going to be 0? No, it's going to be on the range of around what? Around 100 millivolts. And that's rule of thumb. So let's see it, and this is saturated. And my thing's not doing too well, guys. You'll gotta bear with me. What about VCC on cutoff? Voltage collector to emitter on cutoff. Voltage collector to emitter, cutoff. What should it approximately measure? Or whatever that we. By the way, this guy has a name, and we talked about the other night. This power supply, we call it VCC, voltage collector power, right? So this should measure approximately VCC. Will it be exactly VCC? No, but it's going to be real close. Okay, y'all follow this? Yes or no? Yeah, but it sounds like it, right? Cutoff makes sense. Cutoff means it's cut off, right? You understand? Yeah, it acts like an open switch. Saturated means you're putting as much current as you could possibly do. This right here controls the saturated current, by the way, that resistor that we put up there. When it drops, when that collector resistor drops all the voltage, the transistor saturated, because it leaves no voltage for the transistor. It'll never drop exactly all the voltage, even though this simulation kind of shows that. So this is the voltage drop across the transistor. The transistor's only dropping 106.32 millivolts. So this guy is saturated, right? You understand that? It's saturated because we're only dropping 100 millivolts across the transistor. While ago, I set this at 5K. If my simulation is still running, it says it is. Let me stop it. The one that we have, they must have a lot of memory available to us. So I didn't want to set it at 5K. I need to go back and redo that. I'm doing that wrong because I'm doing it the way. This is still 10K. Okay. And I'm going to drop 50%. Is the transistor dropping 15 volts? Is it dropping 100 millivolts? It's like, so what region are we in? Active region. So we're operating within the active region, right? So now if I come over here and reduce this, let's say I go to 25%. I'm sorry. We move towards saturation. So let's go So this is 60%, and now it's dropping 5.582 volts. Okay, that's across the committer, voltage to collector. I mean, voltage collector to emitter. So notice as I go down with the voltage, so here's my voltage right here. So I go down with the voltage, then it moves toward cutoff, right? So here's 65%. Okay, we're up to 7.47 volts across the collector. Here's 70%. It's at 9 volts. So y'all see what it's doing now is varying. So my transistor's acting like a rheostat, right? You understand? So as I change this voltage right here, so if the voltage here goes down, the base current goes down. If the base current goes down, the collector current goes down. If the collector current goes down, it drops less voltage. If it drops less voltage, that means there's more voltage drop across the transistor. That makes sense? Yes or no? So if I come up here and take this to 75%, will the transistor voltage go up or would it go down across the transistor? It should go up. So now it's 11 volts, right? Here's 80%. So it's moving toward cutoff, right? You understand? Here's 90%. So it's cut off at 90%. So once I get it cut off, I can't cut it off anymore, right? You understand what I'm saying? So when I go down on my other side, here's 10%. So it's already saturated. See, so we got 100. So once you saturate the transistor, you can't saturate it anymore. It's kind of like a faucet. Once you turn the faucet, once you get the maximum flow, it don't make any difference how much you open the valve past that. You're gonna get the same flow, right? Does that make sense? You need me? So we could literally do our labs on here, you know, instead of hooking up the circuits, we could literally do our labs using multisim. But you got to understand, this is not a circuit. This is a simulation. So the circuit might not respond exactly to the way the real circuit works, but it'll be close. Oops. So let's see. I need to. So I don't know why it won't let me adjust it with a slider, but that worked out okay. So everybody have a pretty good idea of saturation, cutoff, and active. Are you okay? So saturation, it acts like a what? And how much voltage will it drop? A little over, right? Because it's not a closed switch. Around 100 millivolts, right around there. Okay. Then when it's cut off, it acts like a what? Open switch. When it's open, it should drop the applied voltage, whatever the voltage is, right? Close to it. It might not be exact, but it's going to be real close to it. And then in the active region, it acts like a what? It acts like a what? Acts like a rheostat. But it's electronically controlled, right? So the supply voltages have a name. So the collector supply voltage, we refer to that as, the collector supply voltage, we refer to that, and I don't see my markers, we refer to that as what? VCC. The base supply voltage, we call that what? VBB. The measurement, there they are. The measurement that we make between, these are all relative to circuit common. This voltage right here, when we measure this, we'll call this VB. Are you okay? This voltage here, if we make it right now, this voltage here is going to be 0 because we have nothing. But a voltage measure between the emitter and common, we call this what? VE. Are you okay? And the voltage measurement between the collector and common, we call this DC. If we had a emitter power supply, what would it be called? VEE. So your power supplies, you just repeat the same letter, right? Everybody okay? Any questions there? Then we have our measurements across the transistor itself. This shows you, the one on the left, this shows you where you put your black lead at on your meter. These are all DC measurements. So this one is where you'd put your what? Your red lead on your meter. This way you'll get the right polarities. Everybody okay? So we call this voltage base to emitter. That's what we call that. This would be voltage collector to emitter. This is very, very important because this tells us what region we're operating in. So if it's less than a volt, we say the transistor saturated. If it's equal to the applied voltage, then we say it's cut off. If it's somewhere in between, then we say it's active. So this guy right here is very important. Voltage collector to emitter. So you actually measure these voltages on the transistor itself. So we'd put our what? This would be our meter. Your black lead would go right there. Your red lead would go right here. And if this is an NPN, that voltage should be positive. If it was a PNP, it should be negative. Remember, everything that we talked about on an NPN is just opposite on what? A PNP. Everybody okay? So if we measure this voltage and it's conducting, it should be equal to approximately about 7/10 for a silicon transistor, and what for a germanium transistor? About 3/10. Germaniums are not as near as popular as silicon, but they're still out there. Now over here, I'm going to put my black lead right here. Oops. I'm going to put my black lead right here on my meter. And up here, I'm going to put my red lead. Oops, dang it. God, sorry. And what should this measure? Is it going to measure positive voltage or negative voltage? Good, yeah. So this is NPN. But remember, the collector is backwards, right? It's reverse bias. So this should be a lot more positive in respect to that. So this should always be a positive measurement, unless it's saturated. We'll talk about that. So these are very important measurements, right? That makes sense? Everybody okay? Any questions? Then we have our power supply designators. Our power supply designators are VCC, VBB, and VEE. Do y'all understand those? Everybody okay? So these are power supplies. These are not across the transistors. This is just measuring across your power supply. Okay, guys, is this guy operating in saturation? Is it operating in the active region, or is it operating in cutoff? Tell me how we're going to look at this. You're just guessing. How are we going to figure? How are we going? Yeah, but if we get so much base current, and let's assume, well, right now what we're going to do is we're just going to assume a beta of 100. Okay. So what you did is you just assume it was, but If this beta of 100 causes too much current to flow and this guy here drops all that voltage, then it would be operating in saturation. I know it's not operating in cutoff. So I know it's either operating in the active region or it's saturated. So how am I going to figure that out? Well, what I'm going to do is I'm going to come over here. I'm going to take 0.7 volts. I'm going to come over and say 3 volts minus 0.7 volts, which would give me voltage. This will be the VRB. Which is what? 2.3. I'm trying to do this. Okay. Then I'm going to calculate my base current. So my base current, IB, would be equal to 2.3 volts divided by 10K. This gives us IB. Is that okay? 230 microamps. I'm going to take that. I'm going to calculate IC. I'm going to say IC is going to be equal to 230 micro times 100. That's the beta of the transistor, right? That's the gain of it. So that's used to calculate a collector current if we know. Are we okay so far? What laws are we using? We're using nothing but Ohm's law, right? The only thing that we did was that guy right there, the 7/10 of a volt, right? And we need to know the what? Beta. Okay, now I can calculate the voltage drop across RC, VRC. Sorry, guys. VRC would be equal to what? 1K times 223 milli. What's that? You're exactly right. That's exactly right. So you can't drop more than is applied, right? You understand that. So this guy's going to drop 20 volts or around there. So how much is the transistor going to drop? 0. So it's saturated. We saturated this one. Yeah, I know. Yeah. Now that was your guess, right? After we solved the circuit. So how could I keep it from saturating? Yeah, how could I, if I wanted it to be active agent, what would I do to keep it from saturating? I got two options. Yeah, we could check, not both of them, just we wouldn't fight against. I would either make the RB bigger. If I made RB bigger, that would make IB go down, right? You understand? If IB goes down, then we're going to be away from saturation. Or I can make RC smaller. If I make RC smaller, it would drop less voltage at that current, right? Y'all understand that? And so either way, so we got two things to do. But look, all the math, and this is what's so cool. This is basically the math you learned in what? In DC. Another thing we can do, guys, is we could change this voltage. So let's drop it down to 2 volts, and y'all calculate it now. So this is what we're going to be doing. We're going to be bringing a signal in on the base, and in that base, it looks like we're bringing a voltage signal in, but we're bringing a voltage signal in, right? You understand? But this resistor right here is converting that to a what? It's converting it to a current. Because the base isn't looking at a voltage, the base is looking at a current, right? You understand that? So if my input voltage goes down, this resistor is going to drop less voltage. If this resistor drops less voltage, it means base current is going to go down. If base current goes down, the collector current goes down, and this should move us away from saturation. So actually, we have 3 options. The input voltage could be less, right? You understand that? Or we could have increased the size of RB, or we could have decreased the size of RC. But you got to understand, I'm using 23 microamps to control 23 milliamps worth of current. Of course, this will go down, so let's erase this and let y'all do the math for me. Everybody doing the math? Because this sounds like a really good start of class quiz, right? Which we didn't give today, by the way, because Dr. Crawford came in. Y'all have one of those IDs? Y'all get the bell? Y'all need to start wearing them. I don't know what they're going to do if they come in here and you don't have them in. They might kick you off campus. I don't know. And we on this campus we don't have a lot of this campus. We've had a few problems with people just coming off the road up here and just coming in because we don't have a fenced in. Birmingham campus is real bad because they're right next to the high school. Yeah, and all them high school kids like coming over and mingling with these college kids, and so that's why they're really going to start enforcing that. By the way, we're going through accreditation now. We're in the accreditation team should be in here on November. I think it's the weekend of the 15th. So we might have some sure enough big wigs come in. This is a big deal. So we're going through accreditation this year. It's our 10th year. So our college is going through accreditation right now, and it's a lot of work. And so the final stage of the accreditation, so they have to send them all this paperwork. You wouldn't believe what they have to send them to it. And then they actually they put a team together and they come on campus made from other administrators and people from other accredited colleges. And they come in and they make sure that all this paper you submitted is true. Yeah. Well, that's what allows that allows your college your credit to transfer to some colleges, right? Especially your academics. So we're accredited by the same accreditation. We're accredited by SACS, which is the Southern Association of Colleges and Schools. This is the same accreditation that accredits Auburn, UAB, same group. So the only problem y'all have with career tech courses, guys, is there's no college that offers a bachelor's of technology degree. They all offer science degrees. We do have University of West Alabama, where you can get about half of your credit there. We have Athens University that will give you career tech credit. I know UAB doesn't. I know Auburn. At University of Alabama, when we were still Bessemer Tech, they had a bachelor's degree in technology. And the guy that developed it and pushed it, all the big engineers down there, they never liked it. All the engineers teaching in the program, and the guy passed away. And guess what? The first thing they did, they kicked out that program. Sure did. So y'all could have transferred y'all's credits there. So what do? We drop this down to 2 votes. Y'all calculate this for me. So what we want to do is we want to get voltage, collector to emitter. Yeah, but here we're going to use 2 votes instead of 3. Same thing, right? Yeah, so let's go ahead and calculate it. And we use that to calculate IB, and we're going to keep the beta at what? 100. Now, you know, beta is not a real thing. I mean, beta can move around. One of the big things that affects beta is temperature. So as temperature goes up, beta goes up. If temperature goes down, beta goes down. All we know, if this was a 2N3904, all we know is the beta would be somewhere between 30 and 300. That's all we know. But we'll find out later on how we can set the beta, and we can keep it drifting with temperature. So what we'll do is next class we'll actually hook this circuit up, and then what we'll do is we'll bring a soldering iron up against the transistor, and you'll see the transistor moves towards saturation. And then we'll hit it with some freeze spray, and you'll see it moves toward, it'll move toward cutoff. So this is the problem we have with these things, is that if we operate them in the active region, they're going to be very susceptible to temperature. If we don't do what? If we don't do something. And later on, we'll find out how we can actually stabilize this thing so it works really, really well. All right, guys. So what do y'all got for VB? No, VB, voltage on the base, 1.3. And then what do y'all get for IB? Yeah, right. That's it. That's everybody okay so far? So what would IC equal to? Times 100, because this is the beta. So the beta is the understand that, and hopefully you can see I'm putting 130 microamps in the base, and I'm getting 13 milliamps out of the collector, right? You understand that? Now the emitter current is going to be a little higher, but what we're going to assume, guys, is they're so close to each other. Remember how close they were to each other? So for all practical purposes, we're going to assume, unless we give out a question, if I say IE is equal to IC, what are you going to say? Is that going to be true or false? That's going to be false. If I say it's approximately equal, then that would be true. So watch out for that on tests, because they are not equal. IE is slightly higher than what? Yeah. So what would my voltage across RC be? Yeah, that's what we have to calculate with what's that? 13 volts. So what would my voltage collector to emitter be? Exactly right. Good call. It's going to be whatever's left, right? So what region are we operating in? Active region, no doubt about it. Good job. So basically, rule of thumb, if VCE is less than a volt, we say it's saturated, right? If VCE is equal or close to VCC, we say it's cut off. If That's right. Well, what we did, if this guy right here is driving, so Kirchhoff's voltage law says the sums of the voltages have to equal, the sums of the voltage drops in a series circuit have to equal to the applied voltage. So we come up here and we said this resistor is dropping what? 13 volts. So what is the transistor dropping? It's got to do 7. And we call that voltage. This is what we call that voltage. We call it voltage. Subtract it to get VCE. Yeah. To get what's across the transistor. Now this guy here we're going to have problems with, because this is going to be very susceptible to temperature. And we'll see that next class. When I take a soldering iron and bring it up against this transistor, we're going to use a 3904, which has a beta of roughly 100. And we're going to hook up this circuit right here, right? And then not 3 volts, because we know if we put 3 volts, it's going to saturate, right? We'll put 2 volts into it. And then what we'll do is we'll bring a soldering iron up against it, and we'll see the voltage drop across this we'll see VRC go up and VCE will go down. When I cool it down, we'll see it go in the other way. So this guy right here, right now, if we don't do anything, and this is why, by the way, this is why semiconductor devices have to be cooled, right? You understand? You don't see very many high-powered semiconductor devices that don't have heat sinks, that don't have cooling fans. We can go over there to every one of those robots, and you hear the cooling fans running, because those have a lot of semiconductor devices. Now, what we're going to do is we're going to figure out later on what we can do to stabilize this thing for temperature, which is really, really cool, how we do that. So any questions? So let's do another one more. And we'll use the same beta. So right now we're using absolute betas. And later on we'll figure out how we can actually set the beta. So we want to go down. We don't want to go up. So let's come up here and put 1 volt. And we'll still use a beta right now. Just for math capabilities, we'll use a beta of 100. So what do you say? VB would equal to what? So VB is what? 0.3. And what did you say? Yeah. So my VB would be that. My IB would be equal to what? In fact, 0.3. If we don't have, so what would? Well, it's going to be approximately 0. There's going to be a little bit of current, right? You understand, but not enough. Yeah, close to. We can't say it's equal to. It's going to be approximate. There is going to be current flow, right? Y'all understand? So what would my collector current be? What's the matter? That means it's time that we start talking about leaving, right? Yeah, it's going to be approximately 0, right? So what's VRC going to be? Zero. So what's VCE going to be? If this guy's dropping 0 volts, I have 20 volts applied. That guy's dropping 0 volts, which is not. It's going to be approximately. How much voltage is left over for the transistor? Yeah. So this is what we're talking about, guys. If you see VCE is equal to the applied voltage, the transistor is cut off. If you see it less than 1 volt, it is probably saturated. If it's between 1 volt and what? And VCC, it's in the active region. So we just cut that thing off. Now in digital, what are we switching the transistor between? On digital, we're switching it between what? Cut off and saturation. If we're going to use this as a switch, we're going to switch it between cut off and saturation, right? You understand that? If we're using it as an amplifier, then we're going to operate it in the active region. So on your stereos out there, that's going to be in the active region, right? But you're seeing we can put a very small input into it to control a lot of current on the output. This guy's only got a beta of 100, and it can only handle so much base current because it's a little tiny transistor, right? You understand? We get into this guy. We got a 3052 and 3055 out there. That sucker is a 30 amp transistor. That sucker can handle 30 amps when you saturate it, and it's in a TO3. That sucker is going to have to be heat sinked, right? You understand that? So what they try to do is they try to put it on a package where we can mount it, but then they want to make the package as small as possible. If it can't dissipate the amount of heat, then we'll have to mount it on a heat sink, right? And the heat's going to be. But that guy right there, this is a 2N 6752. We could look that up, but a 2N 3055 is a 30 amp transistor, which means if you saturate that sucker, it could run a DC load up to what? 30 amps. So we'll look at the difference in the rating. So the maximum current occurs at saturation. And then after that, when we in active region, we're going to be looking at the power the transistor can dissipate. So if you exceed the power rating, then the transistor is going to burn up too, right? So we'll look at some of those. All right, guys. See y'all next week. When's our next test? Next Tuesday. Okay, so I'll put a review up there. It is next Tuesday. I just tied my